This video is not regarding drones. So if you're looking for drone related stuff, you may consider skipping this one. Shagnik from the future here. This is how the robot will look like once it's completed. Looks quite professional and factory made in my opinion. Well, if this inspired you to watch the rest of the video, let's get started. So I just bought a ton of parts from several websites for my upcoming build, which is regarding an advanced PID based line following robot, and there were quite a few DMs asking how to make one. While it's quite a lengthy process and this is probably the 7th or 8th line follower that I'm building, it's not possible to explain every bit of building the robot within a single video. However, I thought why not make a quick video to show you guys how I build one and make the robot come to life, especially because I'm using a lot of manufactured parts like printed circuit boards, 3D printed parts for this particular project. So without wasting any more time, join me on my journey of building my line following robot, which was built entirely from scratch by myself. Well, first of all, let us discuss what kind of essential components do we need to build any kind of autonomous robot in general. We need a sensor which collects information from the surroundings of the arena in which the bot is placed in. Next, we need a microcontroller which receives these readings from the sensor, processes it, applies necessary control algorithm, and then instructs the other drivers or necessary components within the robot to act accordingly. We need some actuators like motors, solenoid valves, servos, etc. etc. Of course, we do need some additional circuitry to drive them, such as a motor driver. In order to club all these together, of course, we need a good chassis for our robot. And in order to club all the electronic components into one board, we do need either a breadboard, which is not recommended in my opinion for long-term use, or we could use a perf board by hand soldering that. In this case, we'll be using a PCB, that is a printed circuit board, where I have already created the design of the PCB, sent it to the manufacturer, and got it manufactured for my robot. So this is how the PCBs look like, and I have designed these PCBs in EasyEDA and got it manufactured from a manufacturer. That was Robo in my case, and this is how the PCBs turned out. I think these are quite good, especially the finishing and all, along with the details of the text that are present over the cell screen. Nevertheless, I'll be using this particular setup as compared to this which I was using before, which was hand soldered perf board, which takes quite a lot of time to solder and it's a very tedious and time consuming process. Nevertheless, unless you are totally sure about your circuit design, I highly recommend you to not go into designing PCBs because these costs money and you don't want to end up with manufactured PCBs that are of no use collecting dust around your desk. So be absolutely sure about your design before getting your PCBs manufactured. Let's move on to soldering the PCBs with the necessary components. Well, this is a quick video showing the soldering of components within the PCB. It was not possible for me to record each and every step of soldering because it would be a highly time consuming process. However, it's pretty simple. We just need to make sure that our soldering iron is of the correct temperature. I was using somewhere around 360 degrees centigrade. Giving a too high temperature, somewhere around 450, can easily damage your pads, especially as delicate as these, and giving too low of a temperature can result in cold joints. Also, we need to make sure that the soldering flux and the soldering wire that we're using are of good quality in order to ensure good quality soldering. Now, after soldering, we end up with something like this. These are the already hand soldered PCB boards, which is ready to be put into our robot. I have done 2 of them just in case I mess one up. Now we need to figure a lot of other things out, including how the sensor will interact with this particular board, because the port that I have provided over here is a 4-pin port, namely the positive, negative, serial clock and serial data, which basically suggests that it operates on the I2C protocol. And for operating things on I2C protocol, we need something known as a GPIO expander. Now there are 2 types of GPIO expanders that a person can use in this particular situation. Number 1, we can either use a 8-bit GPIO expander, well, 2 of them daisy chained with one another to give us a total 16-bit of resolution, which I was using before. And if I find some kind of a picture of my previous bot, I will put it right here. So that kind of a setup definitely works because it worked for me in the past. But in this particular case, I ordered this. This is the PCF8575 GPIO expander, basically an I2C GPIO expander, but it has a 16-bit resolution by itself. That means that this particular breakout board can have 16 different addressable IO pins. And the sensor array we are using has 12 sensors, the TCRT 5000 sensors. And hence we will be using only 12 out of those 16 pins. Now the question might arise, why we are using a 16-bit GPIO expander? Why not a 12? Well, because it's not easily available on the market. That's it. Coincidentally, while recording this video, I just received the sensors from Hyperdrive, the 12 channel sensor. Well, Hyperdrive is an autonomous robotics community based in Kolkata, and they manufacture sensors to be used in line following robots, and that is the sensor that I'll be using for this particular project. Let's unbox this and I'll be showing you guys how the sensor looks. Alright, so this is the 12 channel IR sensor from Hyperdrive, which we'll be using for our bots build. It's based on the TCRT 5000 series IR sensors is what I believe it is, along with nicely soldered potentiometers and op amps within this particular sensor. Well, I didn't look at the clock recording the video and it's almost 3 o'clock in the afternoon. See you guys after a quick lunch break. So I spent the last 2 hours designing this simple baseboard of our chassis, and I converted that to a simple 3D design in this CAD software. The motor brackets, which I already 3D printed in PETG filament in black color, and this turned out to be quite nice. This is used to hold the motors, the GB37 motors, along with the motor hub that I also 3D printed and I can't find right now, to measure if the wheel that I'm about to 3D print perfectly fits this kind of motor shaft. This is a 6 mm motor shaft. Now let's get on to design the top plate, and also let us accurately measure and insert the holes that will be there in the base plate for inserting the components. As of now, I have only made the holes for accommodating the lines sensor array, that is the 12 channel IR line sensor, that is this one. So apart from that, there will be quite a few other components as well. For example, this motor bracket mount, which also needs screw holes for inserting the nuts and bolts, the spacers for ultimately mounting the top plate on which our PCB will be mounted on the robot. So yeah, let's finalize the design and then we'll get to printing this part real quick. So it's the next day and I just got the 3D printed parts printed from my friend Rick, and there has been a couple of iterations through which I have gone to determine what settings works best for this particular project and what kind of other dimensions that I need to change in order to take into account the practical aspect of the bot being able to perform well in the tracks. First of all, we had this particular motor mount design where the base was actually quite thin. It was around 2 mm thick, which made it crack easily under a little bit of force that I applied in order to test its durability. Hence I came up with this particular design, just a modified version of this one, which had a thicker base, and it survived the same test that I did with this one. So I call that a pass, and hence I printed 2 of those to accommodate my motors. These are side shaft motors, GB37 side shaft motors. So this is how it looks. For the base plate, I just printed the first 2 or 3 layers in order to get a rough estimate of how the design will turn out. This is what came out of the printer. Yeah, quite flimsy, but what can you expect with just 2 layers of print height? But according to the tests, it fits the sensor quite well, which I'm mounting right over here. The screws are on point, everything is on point except for the hole for mounting the caster wheels, because the caster wheel that I am particularly using has a bit wider diameter in the beginning, which narrows down as we go below. So that is something that I did not take into account. I'll be making the slight changes needed for the design and then we'll be going for the final print. So this is our setup as of now. We have 2 I2C devices, namely the OLED display along with the PCF8575 16-bit GPIO expander. So I was quickly running the I2C scanning test in my laptop to see if it detects the presence of these 2 devices, and it does detect it. One is detected at 0x20, another is detected at 0x3c. That is basically the hexadecimal address of these 2 devices, and the address of the PCF is 0x20 and that of the OLED is 0x3c, because I have connected both of these separately and checked which one is getting detected at which address. So let's continue, code this up real quick and make sure that the data effectively flows from the sensor to our main board and from our main board to our OLED display. So I won't be discussing about the coding portion in this video because I believe it's a huge topic by itself and needs special attention. After uploading the code to the main board, I quickly checked for any errors that was present in it, fixed them, and got straight to the assembly of my bot with the 3D printed parts and the electronic components I had laying around. Here is a quick time lapse of me assembling my robot, after which I encountered a unique problem for which I had to reprint the 3D printed wheels. So let's dive into that. So while designing this wheel, I just messed up a little bit because the shaft diameter that it has within it is a little bit more thicker than it needs to be. Hence, it's not a snug fit and there is a significant air gap between the shaft and the wheelbase. Hence, I had to redesign this one, and now the shaft width is perfect and is ready to fit into our motors. However, I do not want to waste this particular wheel. Hence, I designed this, which is basically an adapter which needs to be put into this one and then hammered into place for making it a snug fit. And yeah, then we can use it just like a normal wheel. So let's do that real quick. Perfect. So now this particular shaft is of perfect width to be used within our robot. Now that our build is complete, this is the final product. It looks quite professional and something out of a factory in my opinion. The chassis, the wheels, the motor mounts, the spacers, everything is 3D designed and 3D printed along with this custom PCB which has been designed and manufactured. So it looks quite professional in my opinion and it performs as expected. However, it needs a lot of tuning in order to make it run to its maximum potential, and I just can't wait to make it run on tracks of several competitions all across my hometown, and I'll be uploading those videos soon if possible. So stay tuned for that, and hopefully you guys like this particular build video of mine. If you did, make sure you drop a like, subscribe this channel for more such content, and I'll see you guys in the next one. Goodbye.